Hello class, this is my Project 1 final presentation. My final presentation is on the quality control circuit board inspection. These are the circuit boards that we developed here and they're handmade, so we have a lot of failure rates, a high failure rate. So we have 3 voltage regulators, and what I'm going to be doing is testing these to make sure that they're working properly. My agenda, we're going to go over the history, the parts list, the schematic, safety input, the voltage divider, the calibration, the sketch program, any issues that I had, the bibliography, and then my demo. I gave you the history already. Each voltage regulator has a different voltage, has a 5-volt output, a 12-volt output, and a 15-volt output. And what's unique about these regulators, they have anywhere from 2 volts to 30 volts range output, and it's all based on what resistors you put in there, Ohm's law. So it can easily be changed. If there's an error, if a resistor was placed in the wrong one, you'd get the wrong voltage output. It has a 24 volt voltage input, so we'll be testing that. My parts list, I have just a AC to DC 24 volt power supply that will be supplying the 24 volts. Of course, the Arduino, the LCD screen, we have some Zener diodes and a lot of resistors and some potentiometer resistors, some variable resistors, and some green LEDs as indicators to let us know that it's working. Here's my schematic. Here's the actual voltage divider circuit here. That way we don't overshoot on the 5 volts going into the actual Arduino. On this side of the schematic, we have a Zener diode that will actually protect the LED and actually a current limiter for a resistor for the LED itself. And then on this side is just the LCD screen hooked up to the Arduino. The Arduino safety inputs. So one of the things that I had to do was consider the safety for the Arduino, not to make sure that we didn't burn it out. So what I did did voltage dividers, so that way I can control how much voltage is going into the system. So what I did was I set it up for a max input of 30 volts. So that way on my voltage divider, I would have a max output on the voltage divider, 5 volts. So the reason I set it up for 30 volts is because I knew I was using a 24 volt input, so we shouldn't go higher than that. And then the regulators themselves are regulated up to 30 volts. So if you see the max that I'll be putting into the voltage divider is 15 volts, so the voltage divider equation times the 15 volts, the max I should be getting out is 2.5 volts out of the voltage divider circuit. So I should be putting in a max of 2.5 volts into the Arduino, so we're safe. Let's see. Simple voltage divider circuit formula. I wanted to show you guys this because these values are going to be very important because these are theoretical. So on the next page, we're going to use these values to show you a comparison. So on the calibration setup, these are the same voltage divider voltages coming out. So if you see that 5 volts going in, and then we have 0.833 volts coming out on the voltage divider, our ratio is 1:6. So same thing, so our ratio is 1:6 on all of them based on theoretical calculations. On our measured side, this is where we have to actually watch what we're doing because this is actually part of setting up the calibration. So what I did was I actually use a calibrated benchtop power supply to input into my circuit so I can get my actual calibration values here. And if you can see that these are all 6s for theoretical, but calibration I was getting different values. And the reason is because if I put in 5 volts exactly from my power supply, my voltage drop is actually 0.823 instead of 0.833 calculated. Same with the 12 volts. I measured the voltage divider, the voltage drop. I got 1.9 versus theoretical is 2 volts. Same with the 15 volts. I actually measured 2.2 volts over the voltage divider versus 2.5 volts. So this is what I end up getting as a ratio, instead of 1 to 6, I get 1 to 6.8 volts. So this was really important in calibrating the actual setup. So these values here, I'm actually going to use in the code. So here's the calibration setup still. Here's the calculated. So if I got a value of 171, those values come from the actual serial port output. So if you actually have a resolution of 5 volts, that's the max divided by 1024, because it's a 10-bit input, we actually get a resolution of 4.88 millivolts. So if you multiply that by the 171, you end up with 5 volts. That's if we use the 1 to 6 ratio voltage divider. If we come to this side, this is what we're actually getting on the outputs of the analog value. So if you do multiply 4.88 times the 169, in order for me to get the full 5 volts, I had to use that factor there, the 6.075, because that's actual measurement, so that you're actually considering the error in the actual circuit. So for example, here also, this is the resolution, that's the 4.88 millivolts. So this is what we're actually getting the value from the analog signal. Multiply it by that, and multiply it by our actual calibrated value gives us the 15 volts. If we actually were getting this and we use the 6.00 theoretical number, we'd actually be getting like 13 volts. So we wouldn't be getting the real value. So one of the things that the professor said was, the code, we can't just copy the code, or we have to understand what's going on. So I actually wrote this code. It was very simple. I wanted to show you guys, that way we can see what's going on. So here's my analog value. I had to use floating voltages. What that does is it allows us to use a decimal point. It's not a rounded value, it's not a whole number. I had to input the actual liquid crystal.h library so I can actually use the LCD. Here are the pinouts for my LCD that I used. And then where my void setup, where I actually start writing. So the serial began, I wrote that way I can actually see the value of the analog signal. The LCD.begin, that's the actual 16:2 LCD. So here is the actual calculations on the code. So we're actually reading the value of the analog of A0. And then what we're doing is, this is the actual value of the analog number, multiplied by the resolution, which is the 5/24, which is a 4.88 millivolts, times that calibration factor to give us the correct voltage output. And then I added in delays, that way it can just update every second. So it's just a repetitive, same thing, just on A1, the calibration factor for A1, and then here's A2, the analog signal, and here's the calibration number for that one. So there's the serial print again, just sending it to the serial port communication so I can see the actual value. And then here's this actually printing to the LCD screen. You set the cursor and then the number 1 and then the voltage. And same with set the cursor, move it over the same line, move it over, and then there'll be the voltage 2, and then this is the bottom line, so we can actually print the number 3 for voltage 3. Some of the issues that I had was when I was building the circuit, I actually burnt a 1/4 watt resistor. It actually was you could smell it burning. And what happened is, when I did all my calculations, I didn't calculate the power. I took it for granted it was 1/4 watt and less than 1/4 watt. But after calculating it, when I had 15 volts, the max going into it, I was actually running at 1 watt and I had a 1/4 watt resistor. So it was a little hot. So after calculating it, I calculated 1 watt, so I put in a 2 watt resistor. Also, when I was writing the code, I couldn't figure out why I was only getting 1 line of the voltage output reading, so I actually left out the LCD screen. It's a 16:2 screen. So here's my bibliography, and then here's my circuit, and here's my demo. So I'm going to bring it over here. so you guys can see the circuit. So here's the actual LCD screen. There's nothing connected by wires. So you can see that voltage 1 is 0, voltage 2 is 0 volts, voltage 3 is 0 volts. So I actually have a 24 volt power here. We'll actually hook it up to 24 volts and then plug in our header connector here. And you'll see the LEDs all go on just to let you know that they're on. And after a second, it updated. So voltage 1 regulator is 5.3 volts. Voltage regulator 2 is at 12 volts. That's what we want. And voltage regulator 3 is at 14.7 volts. So this actual PCB is actually working perfect just the way it's meant to be. So what we're going to do next is actually put one on that is not working. So we'll disconnect this. You see all the LEDs go off. This will update. So you'll see everything go back to 0, 0, 0, 0. And let's plug in this other one. I know 2 of the voltage regulators are bad. So we'll plug in this one. And after a second, you'll see these ones update. So you'll see that voltage regulator 1 doesn't work, voltage regulator 2 doesn't work, and then at the same time, the LCD output is voltage regulator 1 is 0 volts, number 2 is 0 volts, number 3 is 15.9 volts. So we know that this one's bad. And you can see the whole reason of this project was to be able to test these boards efficiently, which means in the manufacturing environment, you want to be able to do it fast, no wasted time. And you can see that it took me not even 10 seconds to test this board and 1 second to update the new board, and we know it's good. Otherwise, this would have taken someone 30 minutes to an hour to hook up to a bench that had an actual power supply. They have to make sure it had 24 volt output and then measure each pin. So you can see I take a long time to set up. And like I said before, a lot of our operators ain't familiar with benchtop equipment, but they can easily just move these around and test the boards as fast as that. So you can see that now that board is bad. Everything updated, 0, 0, 15 volts. So what they would do with this board is they would let the engineer know that voltage 1 regulator and voltage 2 was bad, and either the engineer can decide if they want to troubleshoot it, but sometimes it's too long wasted time for an engineer to troubleshoot every component, and it's easier just to get a whole new board. So that's my project. I hope you guys liked it, and I look forward to seeing yours. Thank you.